Hi everyone, my name is Liza. I am a PhD student of University of São Paulo, and I will present a part of my PhD research in stability analysis area. So this work is called matrix method for stability analysis of a non-Newtonian fluid flow and consists to present a way to make the stability analysis. The presentation was divided this form. So I'll talk about the motivations and the goals that of this work. Sorry. I will show the mathematical formulation needed behind these methods. I will present the results obtained using these methods, and I will talk about the conclusions that we can make. The study of hydrodynamic stability has the purpose to find out if a given flow is stable or unstable, and if so, how this instability could cause the development of the turbulence. There are not many works in this area, so the purpose of this work is make contributions in this sense. So this work has the goal, sorry, to present a way to obtain the results in stability analysis of viscoelastic fluid flow in a more simplified way. The equations needed to make the stability analysis are the continuity equation, the Navier-Stokes equation, and the equation for the constitutive model. In this work was used the Oldright B model. Uh, the stability analysis is carried out by means of linear stability theory. So to use this theory, this formulation is needed to make the algebraic manipulations on the equation system. So applying all the hypotheses needed to use the linear stability theory is obtained this system of equation where equation 5 is the continuity equation, the equation 6 and 7 are the Navier-Stokes equation, and the equation 8, 9, and 10 are the constitutive model. The matrix method consists to rewrite the system to solve the eigenvalue problem associated as presented in equation 11. To, to rewrite this system of equation as equation 11 present, it is necessary to use the eigenvector as presented in 12. The derivative in the equation system are approximated by the Chebyshev polynomials as proposed by Orzagi and Walter-Perger. And the eigenvalue problem was solved in this work using the eigenfunction on MATLAB software. The table 1 shows how the instabilities are classified using the LST technique. In this work, we only made the spatial analysis, but the temporal analysis, it can be done using this method. When we apply the hypothesis to use the LST technique, it's necessary to decompose the variables of the fluid flow in a basic flow and the fluctuations. The basic flow for Oldright B model in a flow between two parallel plates, it can be obtained using the analytical expressions presented in equation 13, 14, and 15. So the results were divided into two parts. The first part is presented the verification of the results obtained in this work. And the second part was made the variation of the dimensionless parameter to show the efficiency of this method to obtain results in the stability analysis. The table 2 shows the comparison between results presented in the literature and the results obtained in this work. The literature was presented results for DNS and LST technique. And this work, we only use the LST technique. It's possible to see a good agreement between the results presented in the table 2 and the results obtained in this work was obtained by taking 150 Chebyshev modes. Here there is a comparison between neutral curves, one by taking in the literature and one obtained using this work, using the formulation presented here. It's possible to see a good agreement between the curves. Here there is another comparison for a low value of beta and Weisenberg 14. And here another comparison for beta more closer to 1 and Weisenberg 8. Here is presented a variation for Weisenberg number for different values of beta. It's possible to see the Weisenberg effect on the instability region. So as Weisenberg is increased, the instability region increases and then decreases. It happens for beta 0.125, 0.25, and 0.5. For beta 0.875, it doesn't happen. Here there is a few curves now varying the constant beta for different values of Weisenberg. So we simulated for Weisenberg 2, Weisenberg 6, and Weisenberg 14. And it's possible to see the effect of the constant beta on the instability region. So as beta is increased, the instability region decreases. And it happens for all the Weisenberg simulated. All the results presented in this work it can be seen also in the reference article. We simulate the same results that presented in the reference because we want to see if the behavior of the results obtained in this work was the same behavior presented in the reference, and it was. So this is show to us that this method is efficient to get the instability results. The results presented in the reference was taken by solving the Orr-Sommerfeld equation using the shooting method for the eigenvalue problem. The disadvantage to use this method is that to get the results, the correct results, is necessary to use a relatively close initial guess so that your method can converge for the right solution. And in the formulation presented in this work, it's not necessary because we solve using the matrix method, and the entire eigenspectrum of solution is obtained. And the challenge here is to find the smallest one, which carries the instability information. Here is the reference using this work. The reference used to compare the results is the 31, DNS and LST stability analysis of 100 dB fluid in a flow between two parallel plates, and was published in 2019. Here are our acknowledgements. So to CAPES, to ICMC USP, FAPESP, CMI, and thank you for watching.